Okay, so, but chapter 11 is on amines, and we've already defined amines. Again, I differ from quite a few textbooks in terms of how they list out functional groups, but I really think this is the best way to define the amine functional group. We said that amines are an organic derivative of ammonia. By organic, I mean that because of this alkyl group over here, there's some significant percentage of carbon and hydrogen. And like we said the first day of class, I don't know that I can give you an exact number above which a molecule goes from being inorganic to being, or goes from being inorganic to being organic, due to the percentage content by weight, let's say, of carbon and hydrogen. But even just a methyl group will be enough. That's the smallest possible amine. So methylamine, you need at least the one carbon to get an amine. These two other bonds can be to either hydrogens or other alkyl groups. And if there's multiple alkyl groups, they can be the same or different. And you'll still have an amine. Amines can also be cyclic. And mostly today, I'd like to go over the various structural possibilities that you'll find with amines, help you to learn how to classify amines. They basically fall into three categories: primary, secondary, tertiary. Let's try hydration of blood and see if we get diastereomers or enantiomers. And well, you know, we'd have to, if I have time, I'll do that problem and I'll show you what you have to know to get it right. And I'll go over the facts that are relevant, if we have time, which we very well might. Good. So this, I think, is the best definition of, the best and most general definition of an amine. You do need at least one alkyl group, right? Because if they're all three hydrogens, then you've got ammonia. And ammonia is not organic. There's no carbon in it. So again, I suppose the smallest possible amine is methylamine, CH3NH2. And by the way, naming amines is generally pretty straightforward. I think it's kind of a boring thing to lecture on, and an even more boring thing to listen to a lecture on. But we'll do some examples of amine nomenclature. But again, as I've said many times, if you know how to name alkanes, you've got 90% at least of what you need to know to name any other kind of compound. So I think no one will be shocked that this compound, for instance, is methylamine. No big surprise. Other examples maybe of common amines. What about this one? So you still need to know your alkyl groups. If you need to go back and review them, that's fine, but you need to know that these are both isopropyl groups, and this compound can be called simply diisopropyl amine. And I don't care if you memorize these names. The idea is to be able to name amines in general. Diisopropyl amine. And I don't expect you to know it all right now. You'll have to go to your OWL assignment and practice. Diisopropyl amine. And again, it's funny looking with the two I's right next to each other, but that is the correct name. Good. So amines can be cyclic. So that certainly qualifies as an amine. I don't think I really care if you know what it's called. It happens to be called pyridine if you're curious, but these usually have special one-off names, molecules like this. But I would expect you certainly to recognize that as a valid structure in an amine. It's just the nitrogen is included in the ring. Other examples of amines. What if you have three alkyl groups attached? This is a very commonly used amine. You can call that guy triethylamine. Again, no big shock in terms of the name. I bet most of you would have guessed that right off the bat. One special amine that I believe you've already learned the name of in chapter 4 is aniline. Aniline is the common name for aminobenzene, so a benzene ring with an NH2 group on it. Oops. So this compound is aniline, A-N-I-L-I-N-E, aniline. And one could imagine derivatives of this. You could talk about parachloroaniline by putting a chlorine in the 4 position. Substitutions made on the nitrogen are used with a capital N to name them. So for example, if we replaced, let's say we replaced both of those hydrogens with methyls. CH3 taken twice. You would call that, and I'll write it down, you would call this NN-dimethyl aniline. And that's certainly a well-known and often used compound. NN, capital N's meaning nitrogen. This is telling us that there's 2 methyl groups on that nitrogen. And naturally, if we had, let's say we had replaced just one of those 2 hydrogens with a methyl group, so this were NH-methyl over here, that would just be N-methyl aniline. So this is NN-dimethyl aniline. So that's how those things are named. And it's like I said, these aromatic compounds, you run into them so often in structures that include those compounds in part of their structure. It's just really, it's just really important, I would say, to know at least some of those common aromatic compounds. And I don't think the list in chapter 4 is too outrageous. So, but in order to be an amine, we need there to be at least 1 hydrocarbon group attached. There can be 2 or 3. Tryptamine, I don't know the structure of tryptamine. I could probably come up with tryptophan, but I don't think I know tryptamine. I'm sure one could Google that. Well, wait a minute. Maybe I will after I'm done sort of presenting this, but I want to maybe get to some of these stereochemistry questions first, as of first importance over that. So one thing I do need to remind you of, remember that the R group has to be a hydrocarbon group. This absolutely cannot be a carbonyl group directly attached, because if you have a carbonyl group directly attached to a nitrogen, remember this is not an amine, this is an amide. Right, so that's not an amine, that's an amide. That's a different critter. Amides don't have the same reactivity as amines because of that carbonyl group there. And we'll say more about amides as time goes on. But please, whoops, sin unto me, forgetting my lone pairs. And we're beginning to relax those rules, but I think it makes it clearer at the moment. So amides are not amines. Sure, they have some similarities due to having the nitrogen atom, but I would say they have more differences than similarities in their reactivity and behavior. Good, so I think that's all we really need to say about that. It's important to be aware that in addition to possibilities like with pyridine over here, there are scads of other heterocyclic amines. One rather simple one is called pyridine. I don't think I really care if you know that, but pyridine has a structure just like benzene, except that we replace one of the CHs with a nitrogen. And that's a pretty commonly used compound as a solvent and a reagent. It's dreadful, stinks to high heaven. I hate using pyridine. But if you're wondering, it's spelled P-Y-R-I-D-I-N-E. And again, I don't really care if you memorize that name. But if you run across it, that's what it's referring to. But if you're curious about that, then you'll also be curious about pyridine. It's a little longer. P-Y-R-R-O-L-I-D-I-N-E. Pyridine. Did I do that right? Yes, I think that's right. So again, I don't care if you memorize any of these particular heterocycles. Heterocycles like this are going to come in handy, though, when in the very next chapter, we're going to go to nucleic acids next. And there's a method to my madness, if you'll only trust me on this, because after having completed the chapter on amines, you'll know everything you need to know in order to understand other nitrogen-containing heterocycles, like tryptophan, which is an amino acid, so we'll save that for the amino acids chapter. But if I'm careful here, I might be able to draw one of these nitrogen bases of the type that you find in DNA and RNA. I just am not confident that I'll get everything right, but I will try. Yes, I think there's like a carbonyl up here. This may not be exactly one of the nitrogen bases that we find in DNA or RNA, but it's going to be similar. You get interesting heterocycles looking something like this. Wait a minute. Hold on. I don't think there's supposed to be a hydrogen. There's supposed to be a hydrogen. There is supposed to be a hydrogen on this one. So I'm doing something wrong. Let's try this. I just don't have these structures memorized, and I certainly will not expect you guys to memorize them either when we get to them. But let's see if I can make a structure that makes sense. Well, that at least is a structure that makes sense. And again, I'm not entirely certain that this is one of the nitrogen bases that you'd find in DNA or RNA, but they all look something like that. And so we'll have just done a chapter on amines. You'll understand how nitrogens can be in heterocycles as well as in acyclic compounds. And so seeing structures like this is going to be something we're going to be able to understand. And I'll just let you know, for most of these biochem chapters, you're probably not going to be responsible for most of it. I've always been very clear in the class notes. I've said exactly which sections you're not going to have to know about for the exam, and I've spelled it out absolutely explicitly. But the trouble is, your book makes the same decision that I see in really all modern organic chemistry textbooks, and that is that they all include chapters on the biomolecules, which I'm a big fan of them doing, even though I'm not a biochemist. I think it's perfectly reasonable for them to have chapters on carbohydrates and proteins and nucleic acids and lipids and I'm forgetting one. Did I say proteins? Amino acids? Maybe I did have them all. And especially in this class, it's in the title of the class that you're supposed to get some background on biochemistry. But a lot of the material in these chapters isn't chemistry at all. It's molecular biology. It's material that you'll have gotten and for some of it, even in high school biology, and others that you'll be getting in other college courses. And I don't feel it's appropriate to teach that in a chemistry class, never mind that I don't consider myself qualified to do so. There's nothing wrong with that material. I'm not trying to demean it or say anything bad about it. It's just not organic chemistry. So what we're going to do when we get there, and we're going to start getting there pretty soon with the chapter on nucleic acids, is to cover those aspects of those molecules from the perspective of an organic chemist. And what I've found, I've even gotten very positive feedback from students so far, what I've found is that the material we'll be talking about will be exactly the material you will not get in your biology and biochem classes. And this way, you'll be well prepared when you go to those classes. Because we're going to talk here about the same thing we always do: structure, reactivity wherever possible, and mechanism wherever possible. It's always those three things that organic chemists are obsessed with: structure, reactivity, and mechanism. And that's exactly what they're not going to talk about when you get to your biology classes. Again, I'm not trying to demean them. They have a different set of material to cover, and I am not questioning their decision. But if we can cover these molecules from the perspective of, look, we know what an amine is, therefore we can understand things like this. And that's the sort of thing we're going to go over when we get to those chapters. But I'm certainly not going to examine you on replication and transcription, for instance. I think you'll agree with me if you're reasonable. That doesn't belong in this class. That's not organic chemistry. Nothing wrong with it, it's just not organic chemistry. Or in the proteins chapter. You know, I'm not going to go into any great detail about primary, secondary, and tertiary structure of proteins. We're certainly not going to do, oh, do you know all these things whereby they sequence polypeptides? You can treat it with cyanogen bromide and you get these pieces. You can treat it with chymotrypsin, you get X, Y, and Z. And they're actually, they're kind of fun. You guys might enjoy problems like that. It's kind of like solving a puzzle. But again, it's not organic chemistry. But what about what proteins are like structurally, and how can we understand them on the basis of the functional groups we've learned? That's sort of the approach we'll take. Anyway, I kind of took a detour there. What, me go on a tangent? That absolutely never happens. Anyone who knows me would be absolutely shocked at that. But I don't mind it since we have a little bit of extra time. So let's see then. What else do we need to say? Maybe I'll do just a few more examples in terms of names, just so you kind of get the idea. I can't do every single possibility. But even if it's a longer chain, I would call something like this pentylamine rather than aminopentane. I just think pentylamine sounds better. That's normally what people would call this. If it's just one simple alkyl group like that, I think that's the best name. What if there's multiple alkyl groups that are different from one another? Like this compound has a methyl group and a propyl group. Well, just like with alkanes, you'd go in alphabetical order. I think the best name is methyl propyl amine. I don't think we would need to say N-methyl, N-propyl. I think it's understood. But I think that's the best name. The only time you really start having to call amino groups is maybe in complicated compounds with multiple amino groups. Here's a reagent they use quite a bit in making polymers and things like that. It's used as a catalyst, I believe. I'm no polymer chemist, but I'm pretty sure I've heard of something like that. And actually, this goes right into our stereochemistry stuff too. I think it's best to call this guy, and I'll write it down, trans 1,2-diaminocyclohexane. I think that's the clearest, most straightforward way to name that compound. Trans 1,2-diamino, oops. I need to move both me and chat. Cyclohexane. Now, since we've stumbled onto a good chance to do this, what about the stereochemistry here? I hope you would conclude that this compound is chiral because there's no plane of symmetry here. Right, if you tried to put a mirror plane here, this NH2 would get reflected on top on a wedge bond, and the amino group is on a dotted bond. So this compound is chiral. And you're probably going to make me figure out if they're R or S. Oh, for heaven's sake. Okay. Let's see. So the amino group will win, then this carbon, then this carbon. Well, this is one chiral carbon, and here's another. And the way you know that is, again, H, CH2, carbon with a nitrogen attached, and nitrogen, 4 different groups. So I think it will go this way. My hydrogen is blessedly on the back carbon. So that's a right turn. So I think this one is R. And what about this one? Now we've got the hydrogen on a dotted bond. I mean, on a wedge bond. So this wins, then that's number 2, and that's number 3. It's a left turn, but the hydrogen's on the wedge bond, so we change our mind at the last second and we say it's R, even though it's a left turn. Good, so that one's the RR compound. And I believe what you will find in this case is there's 2 chiral carbons, so we expect a maximum of 4 stereoisomers. The way you know that those 2 carbons are chiral is because they fit the definition. They're sp3 hybridized, and they each have 4 different groups attached. So this carbon is quite different from that carbon. That's a CH2, this is not a CH2. So that's how you know they're all different. And again, the way you know that this is a chiral compound is because there's no way you can find a plane of symmetry that will exactly reflect one half of the molecule into the other one. So I believe that in this case, you will, no, I don't believe it, I'm quite certain of it, that you will find that with 2 chiral centers, we expect a maximum of 4 stereoisomers, but in fact, this is going to be one of those cases where there's only 3. This will be one of them, the RR compound, and the SS compound. There are multiple correct ways to draw it, of course, but one way is like this, with a dotted bond here and a wedge bond down here. You can see how I've switched them. So that would be the SS compound. And then lo and behold, when we go to try to draw RS and SR, they're the same thing. And that will be a meso compound. And I think with this, I'm sort of killing 2 birds with 1 stone and maybe getting at some of that stereochemistry stuff at the same time. So this guy would be what? I guess RS. And then if you go try to draw it this way, so these are all different stereoisomers of 1,2-diaminocyclohexane. There's 2 trans stereoisomers, the RR and SS compound. Those 2 are enantiomers. But then RS and SR are the same thing. The way you know that is because if you simply take this molecule and flip it over like this, the NH2 groups on the wedge bonds will then be on dotted bonds. You know that because here they're sticking out at you, and if you just flip it over like this, they'll then be sticking inwards like that. So these 2 are the same compound, they're not enantiomers. And so this was one of those meso compounds. So instead of 4 stereoisomers, there's only 3. And you would have this enantiomeric pair, and those structures are equivalent. This is your meso compound. Make sense? Everyone clear on why those carbons are chiral? And also in the meso compound, those 2 carbons still are chiral, but the compound as a whole is not chiral. This is an example of how you can know that you can put a mirror plane down the center of the molecule here, and then you will reflect one half of the molecule directly onto the other half, because now this amino group is pointing up, and it'll get reflected into another one pointing up. So there's 3 different stereoisomers of 1,2-diaminocyclohexane. The ones that turn out to be RR and SS, the 2 trans stereoisomers, are enantiomers of each other. And then there's a diastereomer of both, that's this meso compound. You could consider it to be RS or SR. So meso compound is also a stereoisomer, right? The definition of stereoisomers is compounds that have the same formula and the same connectivity, but the atoms are permanently arranged differently in 3-dimensional space due to how they're attached to one another. And so any consideration of compounds like this, you're always talking about stereoisomers as opposed to constitutional isomers, in which the connectivities are not all the same. Good. So I need also then to cover, we were going to do, well, I did butylmethylamine. There's other ways of categorizing amines that I'd like you guys to be aware of, simply by the number of hydrogens versus alkyl groups that are attached to the nitrogen. And again, ammonia itself is not organic, but if you've got a nitrogen with 2 hydrogens, so they can be stereoisomers but not chiral centers. Chiral centers is a term that only applies to individual carbon atoms. Do you mean they can be stereoisomers but not all of them are chiral? If that's what you mean, then I agree. That's true. And you can't know that ahead of time. You have to examine the structures. You know, there's no like rule or equation. But anyway, primary amines are of this type. A primary amine, I'm giving you here in pictorial form the definition of a primary amine. It's one in which there's 2 hydrogens in 1 alkyl group attached to the nitrogen. So the simplest primary amine would be methylamine. But pentylamine up here would also be a primary amine. And then a secondary amine would have 1 hydrogen and 2 alkyl groups. And those alkyl groups can be the same or different. So if it's 2 methyl groups or a methyl and an ethyl, we did diisopropyl amine on the previous page. That is a secondary amine. And we also looked at the structure of pyridine. That was the 5-membered ring with the NH in it. That would also be a secondary amine. That falls right into this definition. The only difference is R1 and R2 are connected up into a ring. So that would also count as a secondary amine. And then, as you will no doubt have already guessed, a tertiary amine simply has 3 different R groups, or no hydrogens attached anyway, directly attached anyway, just alkyl groups. And those alkyl groups can be the same or different, doesn't matter. R1, R2, and R3, we call that a tertiary amine. And then, although it's mentioned later in the chapter, I will jump around a little. You will wonder, well, can't you attach 4 groups to nitrogen so that it still has 8 electrons around it? And indeed you can. Certainly that is allowed. However, that's no longer an amine as such, because you'll find that if you do that, the nitrogen winds up with a formal charge of +1. Like this. So R1, R2, R3, R4, and those groups can be all the same or all different, or some same and some different, doesn't matter. And so compounds of this type are actually ions, they're cations, and you can call them either quaternary ammonium salts or quaternary ammonium compounds. I think your book calls them quaternary ammonium compounds. Though quaternary, I usually call them quaternary ammonium salts. But again, not quaternary amine, quaternary ammonium. That UM ending is a sign that you're looking at a cation. Quaternary ammonium salts. Or compounds. CPDS or for compounds. And of course, you would need a counterion associated with that. It'll often be a halide, chloride or bromide maybe. So these things are used a lot. And actually quaternary ammonium salts with, medium to large R groups over here are used quite a bit as catalysts. They're used as something called phase transfer catalysts. So you can actually do a reaction in a system that's partly aqueous and partly organic. As you know, most organic solvents, not all, but most organic solvents don't dissolve in water. You imagine something like gasoline will not dissolve in water. And we wouldn't use gasoline as a solvent, I don't think. But there's certainly other solvents like gasoline, and that will not mix with water, will float on top of water, largely. Most of them are less dense than water. Again, not all, but most of them are. So you could actually do a reaction that has steps that take place in both layers, and then you add something like tetrabutyl ammonium fluoride is a very common phase transfer catalyst. I don't care if you know that particular one. I'm just using it as an example. We call that TBAF for short, tetrabutyl ammonium fluoride. It's kind of a cute name. Good, so those are kind of the possibilities that you'll run into with amines. And then there's also these quaternary ammonium salts. So let me see. I would kind of like to talk a little bit about hydrogen bonding and maybe go as far as alkylation of ammonia to prepare amines. And I think that'll be enough for that. We can use any extra time. I did come up with some reef questions at the last minute. If we're actually running out of time at that point, which I would not be shocked, then I'll just, in fact, why don't I just take attendance now, just in case we don't get to that. And that will be either 10 points, or if we do some reef polling, 8 points, and the other 2 will be questions. I'm just kind of leaving open all of my options. Good, any questions so far on any of that? I mean, I guess I would say if my choice is doing the reef questions that I made at the last minute or answering some of these questions about stereochemistry, I'll choose the latter over the former. And if it just means we take attendance today, I'm okay with that. I would rather make sure that I address these questions if we have extra time. Good. So we've already gone over intermolecular forces. That's a topic from Gen Chem that I think we hit on in chapter 2. And so amines are one of the molecules that has the possibility of undergoing hydrogen bonding, sometimes, right? Certainly primary and secondary amines, because they have that those NH bonds, those are able to act both as hydrogen bond donors and hydrogen bond acceptors. And we're going to see that also when you look at those big heterocyclic amines that we find in DNA and RNA as the nitrogen bases. So, however, certainly, I mean, we can certainly put quaternary ammonium salts. Those are off the table because there isn't even a lone pair anymore on nitrogen. But even a tertiary amine like triethylamine, or what if we took our pyrrolidine again, but instead of having NH, we put an alkyl group on here. That would now be a tertiary amine, right? And yes, that guy will be called N-ethylpyrrolidine. I don't think I really care if you know that it's called that, but I would certainly expect you to recognize that as a tertiary amine and to say, this guy cannot act as a hydrogen bond donor because there's no NH bonds. Nitrogen is only bonded to carbon. Technically, it could act as an H bond acceptor, but not as an H bond donor. But as soon as you have even one hydrogen directly attached to that nitrogen, if we go back to just plain unsubstituted pyrrolidine again, game on. Now this guy can undergo hydrogen bonding both ways, both as an H bond donor and as an H bond acceptor. So exactly like we went over last time. It seems to be those three small electronegative elements, oxygen, nitrogen, and fluorine. And fluorine almost doesn't count because the only hydride you can get is HF, and then you're done because both hydrogen and fluorine can only form one bond. So oxygen and nitrogen are the ones you want to look out for. When they have, they're bonded directly to hydrogen. If you have OH or NH bonds anywhere in the molecule, then you've got the possibility of hydrogen bonding. The reason this can matter is because this will affect the properties of molecules. So if you compared, for instance, propane with ethylamine with ethanol, these three molecules have very similar molecular weights. For propane, it's 44 grams per mole. You could figure that out yourself by adding up all the atomic masses for C3H8, and you'll get 44 grams per mole. Ethylamine, I think, is 45. Yep. And ethanol would be 46 grams per mole. And the reason I'm pointing this out is just to make it clear that we're making, that we have a set here that makes for a very fair comparison between any two of these, because they're all very similar molecules, certainly in terms of molecular weight. So we're very much comparing apples and apples. We've got fair comparisons going on here. But even though the melting points are so similar, the boiling points aren't. Boiling point of propane, and I don't care if you know these numbers, you see I'm looking them up myself, but the boiling point's exceedingly low, minus 42 degrees C, which means this stuff is a gas at room temperature. This stuff is even a gas at 0 degrees, which is where water freezes. You need to cool it all the way down to 42 degrees below 0 Celsius in order to get it to condense from a gas to a liquid. Meanwhile, ethylamine is quite a bit higher. Its boiling point is plus 17 degrees C. And again, I don't expect you to know that. I wouldn't expect you to be able to guess that. What that means, practically speaking, is at room temperature, this stuff would still be a gas. Room temperature in degrees C is round and about the low 20s typically. It's probably 23 or something like that in here. And ethanol even higher still. Let's see, 78. And all of this is due mainly to hydrogen bonding, which propane has none of, ethylamine has some of, and apparently oxygen is even more effective at hydrogen bonding than nitrogen is. So, because you get the boiling point on changing a carbon to a nitrogen, you go up, or what are we going to call that? 42 and 17. Let's call that a temperature increase of 60 degrees rather in the boiling point, and then you win an additional 60 degrees going from the amine to the alcohol. So that's all due to hydrogen bonding, because what this is telling us is in order to get these compounds to go from a gas to a liquid, we need to disrupt those hydrogen bonds. You know, they're going to look something like this. They're not covalent bonds, of course, but they are attractive interactions between multiple molecules. That's why they're called intermolecular forces. And so this could then be attracted to another nitrogen in another molecule. And in fact, it certainly will be, and so on and so on. So you need to disrupt these hydrogen bonds. It's not the same as breaking covalent bonds. This is not a chemical reaction. But it does take energy to get those molecules apart from one another that we don't need for propane, because there's no hydrogen bonding. So that's why propane's boiling point is so low. And again, the idea is not to memorize these numbers, nor would I ever ask you to guess numbers or supply numbers from thin air. But if we're given this data, then we can make some sense of it. It shows that hydrogen bonding is really important, and it can make for drastic changes in a compound's properties, other things being equal. So that much I think at least is worth mentioning. Right, so where are we at? 335, 336. I'm trying to think if I can go on to alkylation of amines and then leave a few minutes to answer that question someone said above. That's what I think I would like to do. Good. Are we okay on hydrogen bonding then? Any questions on that? Actually, I'm trying to think, will I be fine even leaving this till Monday? I probably would be. So let me do this. Someone in chat asked a question. What bet you would be what? I'm going back to 4-methyl-2-hexene, okay? Let me answer that question first, and then I'll kind of set up the whole thing with alkylation of ammonia in order to make amines. The idea is we want to learn how amines are made. And they're actually kind of hard to make, but there are some ways to do it. Idea of this slide, the one I just erased, you mean? That one? The main idea of this slide is the effect of hydrogen bonding on properties of a molecule. That you have no hydrogen bonding in a molecule like propane. Here's two other molecules that are otherwise really similar. They have almost the same molecular weights. So you can't say that any differences in their properties are because they're so different, that they have such different weights or are so differently sized. But look at their boiling points, which again, I don't expect you to memorize, but we go up from -42 to +17 when we change a carbon to a nitrogen. That's the effect of the hydrogen bonding. It says we need to sort of detach the molecules one from another, and that takes energy. In this case, energy to the tune of close to 60 degrees Celsius. And then another 60 going from nitrogen to oxygen, it would seem oxygen is even more effective at hydrogen bonding. So the point of this slide, what you need to know from this slide, is that hydrogen bonding matters. It has directly observable effects on the properties of molecules. And this is just an example. I don't expect you to memorize those numbers. Okay. So I've already forgotten that 4-methyl-2-hexene. Well, for one thing, we're gonna, are you sure you didn't mean 2-methyl-2-hexene? Well, maybe it doesn't matter. So 2-hexene is here, It doesn't say whether that double bond is cis or trans, but you know what? It doesn't really matter. Once we say 4-methyl, we've got two possibilities. It probably isn't saying whether it's R or S, but I'll just pick this one. And here's what you need to know about cases like this. This is something we covered in class on Wednesday. We said that in any given reaction, there's a possibility of starting with an achiral starting material and getting an achiral product. I gave an example of that. It was a reaction we'd already covered. It was hydrogenation of an alkene. And we also said it's possible to start with an achiral starting material, but have a chiral product as a result. And we went over an example of that. Here we're starting with a chiral starting material, and we're now going to do a reaction that could, in principle, also generate a chiral center. And I think that's going to be the case. Now, this carbon is not involved in that reaction. The way you know that is by what we discussed in chapter 3, where we said that hydration of an alkene involves only the two alkene carbons. Nothing else changes as a result of that reaction. And again, the way you know that is how we defined all the players in the reaction. So I think you can see that once we hydrate this guy, I don't think we're going to have time for the reef questions. I'd rather take some time to cover this since people were concerned about this. So I'll just take your attendance, but please do register your attendance if you haven't already. Now, how do we know what's going to happen over the course of the reaction? What you need to know is that when you hydrate a double bond, the double bond turns into a single bond, and one of the carbons gets the H and the other gets the OH. I think it's more reasonable for this one to get the hydrogen since it's a little more crowded. I actually don't think it's such a very good example. But the thing is, we find, not because there's a rule that we memorized, we find just as a result that we can get two possible products. We can get this alcohol or this alcohol. Methyl and hydrogen here. And then yes, if you like, we also still have the hydrogen pointing down over here. You don't have to draw it, but you can. And in this case, my hydrogen and that carbon is pointing up. And then the question is, how do those molecules compare? What are they to each other? And I think you'll agree these molecules are not enantiomers. The way you know that is because the configuration stays the same at this carbon. The definition of enantiomers is that the configuration changes at all chiral carbons. That's the definition of enantiomers. And here it's not changing at all of them, all two of them, if you will. This carbon is the same configuration in both of them, with the hydrogen down and the methyl group up. However, this carbon changes configuration. On one of them, the OH is up, and the other one, the OH is down. So by definition, these are not enantiomers. These are diastereomers. So that is what you need to know in order to answer questions like that. At least if I'm interpreting the question you were asking properly. Does this help? I forget to ask the question at this point. Or are there any other questions on this idea? What is the reason that the wedge bond in the original molecule doesn't change? Excellent question. The way you know that this doesn't change is because this carbon isn't involved in the reaction. And the way you know that is because we know the carbons that are involved are the two alkene carbons. That's how we defined the reaction. And anything outside of that, such as this carbon, isn't involved. The way you know that is we didn't discuss anything else changing, anything else elsewhere in the molecule changing than the two alkene carbons. So from that, you know that any other carbons are going to stay exactly the same. They're not involved in the reaction, and they're just along for the ride. So that's how you know. And that's also the level on which I would suggest you learn some of those reactions. And if you need to go back and review them a bit, that's fine. It's not going to be a waste of your time because this class is cumulative. Good. And I think with that, I'm actually just about out of time. So we'll continue this sort of leisurely treatment of amines, but I think we'll be able to finish up on Monday with reactions of amines and also preparation. I think you said this, but the OH could have also bonded to the third carbon. Well, I'm still not sure that this was quite the right compound. I wonder if maybe they didn't mean to put a methyl group over here or something. In that case, you could get a whole bunch of compounds, right? Because Markovnikov's rule says the OH will go to the more hindered carbon, the more crowded carbon. Oh, actually, I might have done that backwards, didn't I? Maybe it should have gone here. Either way, you get the same answer. But I'm not in love with that particular example. I think it's a little confusing. But I think as long as we restrict it to this type of discussion, it makes some sense, I think. I think you're going to get the same answer regardless. But the point is that here we start with a chiral starting material, and we run a reaction that makes another chiral carbon, not because we memorized it, not because we knew it ahead of time, but because we examined what we were given, and lo and behold, another chiral carbon pops out. There's no rules to memorize. It's all decided on a situational basis. You know, draw the structure of the product. Is there now a chiral carbon? Yes, no. That's what it is. It's not something we memorized beforehand. So if you're thinking you missed something because you're not able to tell what it is beforehand, you haven't missed anything. So that, I think, is good news. Anyway, I have at this point run out of time, so have a great weekend. I will see you all on Monday.